Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on real-life applications of trigonometric functions. In our last lesson, we learned how to use trigonometric functions to solve problems of height and distance, illustrated by right angle and oblique triangles. Today, we will look at the use of trigonometric functions in the fields of navigation and optics. This should be quite interesting, students. I am looking forward to seeing trigonometric functions put to good use. In navigation, directions to and from a reference point are often given in terms of bearings. A bearing is an acute angle between a line of travel or a line of sight and the north-south line. Bearings are usually given as angles that are east or west of the direction north or south. For example, a ship might report that it is traveling south 20 degrees west or north 40 degrees east. In this example, a ship leaves a port and travels 54 kilometers due west. It then changes course and sails 36 kilometers on a bearing of south 33 degrees west. Can we determine how far it is from the port? You can see that we must calculate the distance of line PB. First, we determine the measure of the angle between our two known line lengths by drawing a north-south line that is perpendicular to the east-west line. This gives us a 90-degree angle, which we can add to our bearing of 33 degrees to get 123 degrees. Now that we have the length of two lines and the measure of their interior angle, we can use the law of cosines. The length of PB squared is equal to 54 squared plus 36 squared minus 2 times 54 times 36 times the cosine of 123 degrees. This equals 2,916 plus 1,296 minus 3,080 888 times negative 0.5446. Therefore, the length of PB equals the square root of 6,329.4048. The ship is about 80 kilometers from the port. Now that you have seen how this is calculated, students, please try an activity on your own. Two ships leave from a port, P, at the same time. Ship A travels 40 kilometers in the direction north 60 degrees east. Ship B travels 60 kilometers in the direction south 40 degrees east. What is the distance between the two ships? Here is a small hint on how to begin, students. You can find the interior angle by using the 90-degree angle between north and east and south and east. Please begin now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. If your answer was that ship A is about 66 kilometers from ship B, you are correct. Good work. The first step is to draw a diagram that will represent the ship's locations. By using the 90-degree angle between north and east and south, we can find the measure of the internal angle to be 80 degrees. Now we have the measure of two sides and their internal angle. So, we can use the law of cosines to find the distance between the two ships. Recall, students, that the law of cosines looks like this. The distance between the ships, line AB, is our value of A. The distance ship A travels from port is the value of B, and the distance ship B has traveled is our value of C. Our internal angle of 80 degrees is A. We will substitute these values into the law of cosines equation. Line AB squared equals 40 squared plus 60 squared minus 2 times 40 times 60 multiplied by the cosine of 80 degrees. This equals 1,600 plus 3,600 minus 4,800 times the cosine of 80 degrees, which is 0.1736. The length of AB equals the square root of 4,366.49, which is approximately 66 kilometers. If you have studied physics, students, you will be familiar with Snell's law of refraction. Snell's law states that a light ray is refracted or bent as it passes from one medium into another. If you look at a pencil in a glass of water, you will see that the pencil appears to be bent at the surface of the water. This is Snell's law in action. Snell's law defines the index of refraction, denoted by the Greek letter mu, as the ratio of the sine of alpha over the sine of beta. Alpha represents the angle of incidence where the ray of light enters the second medium. Beta represents the ray of refraction. The index of refraction between air and water is a constant measure of 1.33. If a ray of light passes through water with an angle incidence of 60 degrees, can you determine the angle of refraction? Please use Snell's law to answer the question, students.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Hello, students. Was your answer about 40.6 degrees? If so, well done. To find the angle of refraction, we substitute our known values into Snell's equation. 1.33 is equal to the sine of 60 degrees over the sine of beta. We find that the sine of beta equals the square root of 3 over 2 divided by 1.33. The sine of beta is approximately 0.6511. To solve for beta, we use the inverse sine function. Beta equals approximately 40.6 degrees. I hope you have found today's lesson as interesting and useful as I have, students. Today we have seen how trigonometry can be used to help ships navigate. We have learned that the angles of their bearings can help us to find their distance from a relative point. We have also learned how to use trigonometry to calculate the index of refraction. You may be interested in researching other uses of trigonometric functions on your own. You will be surprised how practical trigonometry really is. Until next time, thank you, teacher. Thank you, students.